Good day, folks. This is tutorial number 27 in a playlist that's called Kinematics Scenario Animation Simulation and 3D Experience. This particular tutorial deals with describing how to deal with a uh, universal joint, okay? And it's specifically universal joint being modeled with the access-based features available in 3D Experience. The only thing is that in this particular tutorial, I do not model the cross pin that is present in a universal joint. We'll do that later on. So the situation that's going to be done is a shaft, two shafts are uh, tied together through the universal joint access-based functionality. And then one of the shafts, the one on the left, is the driven one. The one on the right is the driver one. So the shaft on the right actually, let's say, connected to an engine, it turns, or a motor, it turns, and it's a revolute joint. And the shaft on the left is going through that bearing, and that's a cylindrical joint or a driven joint. If you look at the whole model, the way I'm going to do that is basically I have three parts. There is the ground where the two revolutes and cylindrical joints are part of that, and then there is a driver shaft which is going to be revolute later on. It's going to go into that hole, and a driven shaft which is going to be cylindrical. Uh, and the way these are going to be put together is based on the access-based functionality. That means these coordinate systems, we tie them together somehow, and that basically makes one shaft term and the other one does. Uh, if you looked at the chapter 9 of this document that I wrote about 9 years ago, it deals with modeling universal joint, but it's an old version of 3D Experience. A lot of things have changed since then, and it really pertains to that particular tutorial. So basically, we're going to have a cylindrical joint, as I indicated, and then we have a revolute joint, and it's going to be modeled later. And these two shafts are tied together through, here's the universal one, through two axis system. Now, there is a bunch of buttons here. These buttons, I'm going to be honest with you, in the case of universal joint, there is no documentation on them in the 3D Experiences help. And I mean, the bottom line is that I'm not 100% sure what these things are. Yes, I'll show you later on that what happens when you select one versus the other. But anyway, this is very poorly documented, pretty much none whatsoever. So notice that here what we have is we have a ground, that is where the bearings are, and that is fixed in space. There's a cylindrical one, so a cylindrical joint on the top left corner, a revolute one at the bottom right corner, and then your universal one. And of course, the command is issued. Universal joint don't have any command, but because it's tied to this revolute joint, we can make the revolute turn, and of course, the whole thing is going to move. Okay, cylindrical, revolute, and universal. By the way, the two shafts are identical, so if you want, you can create them as separate parts, or maybe make one, copy and paste it, or you can use the multi-instantiation. Once you create one, then you just create another instance of it and proceed. That's how I'm going to go that. I'll put these two holes here to see the rotation of the two shafts visibly. All right, let's go ahead. Dimensions are not important, so I'll do it as I see convenient here. Okay, I'm in the assembly design interface. So right now I'm going to make one of the shafts. So insert 3D part. I'm going to call this thing the shaft, and shaft, and we're going to make it. Dimensions don't matter here, so I'll just draw a circle and then pattern up. So on that horizontal plane, I will sketch a circle. This is going to be the cross section of that one of the shafts, exit. And I will pad it up by, let's say, 150 millimeters. 150 millimeters. And then I will create a point above this, which is a height of 200. So a point by coordinates 120. This was 150, so I'll make it 200. Good. So there's a point there, and immediately we create a coordinate system, but the origin of it, I'll place it up there. So the actual shaft that I have in mind is from that point all the way down, but I don't have to model the whole thing. Basically, this represents the shaft, and this is the point where the two shafts are engaged as a universal joint. Okay, so let's go. Oh, by the way, while I'm here, I'm going to make a point on this curve, because later on we want to plot some stuff, so create some sensors, etc. So just create any point there. You can see that's right there, all the way to the top, and save it. Now the other shaft is going to be just like that, so I can actually create another one just like that, or do a copy paste, etc. But the alternative is also, if you're at the assembly level, you click on this shaft here, you can make you can instantiate it, and two copies is good enough, so that's good. So basically we have created two identical shafts. This was the original one, this is the one that's duplicate of that instance of it, and we move on. Okay, everything is, the coordinate system is created, the point is created, because these are instances of each other. Whatever you do here is going to reflect that. But let's go and make the ground. So right click, insert 3D part, and I'm going to call this thing the ground. Properties, make this thing the ground, and ground. All right, let's go make it. So double click on it, and basically I want to create something like this. Okay, so just to make my job easier, I will create a vertical plane here, and sketch on it. If this is bothering you, I can hide it right there. So I'm going to create, this is the point that was associated with that thing that I hit. But anyway, so my profile is going to be, I'll go something like that. We can change sizes if you want later on. Okay, so this is going to be the ground, exit. By the way, notice that when I hit one, the other one hit with it, because they were instances of each other. Okay. Now let's see now. Maybe I should bring one of them to the show mode, see how big it is. Let's see. Let's see how. Yeah, that's good. That's good. Okay. Uh, I would prefer if these were a little bit shorter. So let me go back here. Let me go back here. So this one I'm going to make it a little bit shorter, and this one too. All right, exit. Now at the end of these, at these 2 points, I'm going to make place. Let me hide these things one more time. All right. Let me create a plane. This is in the ground, normal to a curve. This is the curve, and it's going to be at that location. So I'm going to draw the bearing here later on, and I do another one, another plane. Again, normal to a curve, the same curve, but the location is right there. All right. So let's go on this plane. I will sketch. Now I will sketch what is going to be my bearing. So let me draw a circle here, something like that, and another one concentric with it. Make sure it is concentric, like that. Exit, and then pad it. Let me do it in the other direction. Yeah, so that's okay. That's fine. Let me just make it shorter, a little bit shorter. 10. Good. So this is one of the bearing. Now I go to the other side, do exactly the same thing. Okay. So circle. Okay. And an outer circle. Okay. Exit. And then pad it. Let's make it 10. Just like the other one. It really does. These dimensions don't mean anything. Okay. Good. All right. So now we're gonna put these things in these shafts in the right places. One more time, I would like to make this thing a little bit shorter. Good. Okay. So where's the other fellow? The other fellow is in hiding. Let's bring it in the front. Okay. Now, oops. Good. Now, instead of creating constraints, what I'm going to do, I'm going to snap these to the right location. But the first thing that we do, we go all the way to the top, all the way to the top, save everything, the assembly level, all right? And then I'm going to fix the ground. So we go to the engineering connection, fix the ground. That's not going to be moving. There's the fixed ground. Let's go ahead and snap this axis to that line. Okay, and I want this point to be right at that junction point. Another snap between this point and that junction point there. All right, very good. Now let's go ahead and do the same thing with the other fellow. So another snap between this axis and that line. And I want this coordinates, this point to be at that junction point. So this point to be at that same junction point. Okay, very good. Okay, so the only thing is that when you compare these drawings, I mean, this guy is down below. Okay, so it doesn't matter. Okay, let's go back here. All right, so we are in business. Let's go ahead and create our joints. Okay. For example, this is going to be cylindrical. This is going to be cylindrical. So you go to cylindrical, and I use the first template because all I want to do axis and axis. So axis of this shaft and the axis of that bearing. And I don't need any of the other ones because they're going to be driven. Okay, good. So that takes care of the cylindrical joint. Now we're going to do a revolute on this side. So go to revolute. And I will use this second template, axis, plane, plane, but as an offset, and then angle to control them. So the axis of this shaft and the axis of that bearing. And as the planes offset this plane to that plane, okay? And as the angle, here you have to be a little bit careful, make sure you pick the stuff that you want. Well, I can control the vertical plane of the shaft, or the horizontal plane of the shaft and the horizontal plane of the bearing. I'm going to be a little bit careful here. So what is this? This one is for the shaft, okay? and I want the corresponding thing from the ground. So here's the ground. Let's see now, that one is the ground, XY plane, right there. See this? Okay, and say okay, and no. All right, save everything. Oh, universal join. Let's do the universal join. Why don't I save this first? And then it's going to be the universal. And the universal, I'm going to use axis to axis, the two axis systems that I created. So for example, it really doesn't matter, this and that. Okay. Now, these are things that you may have to fool around with later on until things work. But let's just leave it the way it is right now. Say okay, and no. Okay. We are pretty much done here. Now we're going to go to mechanical systems design and create the mechanism. Mechanism representation is to get created. And let's check our joints. Okay, that looks good. Say okay, and let's check it out now. Here, look, mechanism player. This is all the cartoon right now. Mechanism player. We want this thing to turn and the other guy to turn with it. If not, we're going to go and check those boxes that I mentioned. You need to do it based on trial and error, pretty much. That's good. One thing I forgot to do is to draw those holes there so that you can actually see the reset this thing, say close. Let me go to this shaft and draw one of those holes on the sides. So if you go, for example, to this part on a convenient plane, for example, on this plane, I will sketch. Actually, the other one, exit. Let me try another one on this plane. Let me see. Yeah, that's good. Whoa. Let me draw a circle here and make a pocket. We're going to make a pocket later on, just so that we can see things are turning. Okay, we make a pocket. Very good. The pocket is going to come up in both of these because these are instances of each other, as you can see. So go back here one more time, cartoon, no physics. You can see that as this thing turns, the other one turns too. So that's what the universal joint is. Now we're going to put some physics into this. And what do I mean by putting physics? First of all, if you want to hide any of these planes, there's no problem. You can do control F. All the planes, plane, find and select, search and select, and then hide it. It's going to be cleaner. Okay. And of course, this access system, I don't want to hide it. It's fine. Yeah, you can if you want, but I don't want to do that. So now we're going to go and create, to put some physics into the problem. You're going to go to the mechanical systems experience. Say okay. Okay. Just give it a minute. All right. We're going to put some laws. So law of excitation, law excitation. Now for the support, you have to select this command here and a formula. Type in a formula. So for example, you can say this is equal to obviously 0 plus, let's make it 360 degrees per second. So 360 DEG underscore S times time. Now you could have typed here 60 turn per minute and then times that. It's okay. Now there's physics here because we're specifying the velocity or the angular velocity of this shaft. Okay, revolute joint. So we say okay and say okay. Let's do it over a 3-second, maybe 3-second interval. So we create a kinematic. Oh, well, let's do our probes. Probe. See that? Position probe. Now remember, we created these points here, so let me go and select one of the points. It's over there. Okay, this is the point that I created. This is the point that I created on the boundary of that shaft. This is one of them. And let's do another one for the other fellow. Another probe for the other. We did this. Where's the other guy? Uh, oh, there's the other shaft right there. That fellow. So okay. And now we go and do a kinematic scenario. This is the law of excitation over a 3-second interval. Let's do a 3-second interval and make this thing smaller, 0.01. And for the probe, these two, one of them is for the driver, the other is the driven shaft. Say okay. And now we're going to run it. Time. Obviously 3 turns. Okay, let's plot the result. Let's plot uh, the angular velocity of this shaft, the driven one, the driver one, and the driven. Driver one should be constant. Driven one will not be constant. That's the way universal joints work. So let's see, deselect everything. Let's do for the first probe, that is going to be angular velocity. This is for the first one of them. And the other one is number 2, angular velocity. This is for the second one. One of them is going to be constant, the other one should be sinus, some kind of a periodic one. And there we are. Okay. And this is, remember, this was 360 degrees per second, the input. And the other shaft, the driven shaft, is not going to have constant velocity. This is why people use actually constant velocity joints in order to get a constant velocity of the driven shaft. But anyway, that's not what we're doing here. So the next tutorial is going to be repeating the same problem, except that I will create the pin, the cross pin, and make sure it really looks like a and cross pin is in motion, and make sure it really looks like a universal joint. All right, folks, good luck.